Our next presentation is entitled Field Phenotyping of Leaf Spot Diseases and Yield in Groundnut Using Photogrammetry and Vegetation Indices. And Emmanuel Sie will be our presenter this morning or this afternoon, wherever you may be. Thank you, Emmanuel.
Good afternoon. My name is Emmanuel Sie, presenting on the topic Field Phenotyping of Leaf Spot Diseases and Yield in Groundnut Using Photogrammetry and Vegetation Indices. I am an MPhil student from the University of Ghana, studying MPhil plant breeding and genetics. I'm going to be from background, justification through to future research recommendations. Background. Groundnut is an essential crop in Ghana. It is high protein content of 12 to 66%, high oil content of 36 to 54%, and other valuable macronutrients. Groundnut also provides farmers in Ghana with higher earnings than the cereals, making it one of the important crops when it comes to poverty alleviation. However, the production of groundnut is hindered by several biotic and abiotic, which includes diseases, drought, and low quality seeds. So to increase production in Ghana means we have to go for varieties that are resistant or tolerant to these diseases, of which early and late leaf spots disease of groundnut is part. To come with these resistant genotypes means we have to do efficient phenotyping as well as genotyping in order to develop these high. However, the current manual phenotyping methods are error-prone, labor-intensive, they are subjective and destructive. For that matter, we have new techniques which will take care of these challenges that the manual phenotyping methods poses. So we are looking for application of photogrammetry for phenotyping, which is more accurate, it saves time, is non-destructive, and offers direct storage of data. Photogrammetry has successfully been used for groundnut phenotyping in Virginia. It has also been used for leaf spot diseases phenotyping in Egypt. However, its effectiveness has never been tried in Ghana. So the hypothesis for the study is photogrammetry can estimate groundnut leaf spot diseases and yield components in the Ghanaian environment. The main objective of the study is to explore the effectiveness of using photogrammetry, high-throughput phenotyping tool when it comes to the estimation of leaf spot diseases as well as yield components in groundnut. The specific objectives are: one, to determine the efficiency of using photogrammetry as phenotyping tool to estimate leaf spot diseases in groundnut. To determine the effectiveness of applying photogrammetry as phenotyping tool and estimating yield components in groundnut. And three, to determine the group stage at which photogrammetry as phenotyping tool would be better estimate the leaf spot diseases in groundnut. Materials and methods. This study was conducted in Yampala using 60 peanut genotypes, which were obtained from the African germplasm collection. The design used was lattice, repeated 3 times. A row was made up of 1 of length 2 meters long. Spacing was 0.5 between rows and 0.2 meters between plants. Data was collected on the parameters at 85 and 95 days after planting. The parameters collected were NDVI readings, which is the normalized different vegetation index, imaging, visual disease scoring, pod yield per plant, of course, per plant. Early leaf spot disease and late leaf spots evaluation was done using the Florida scale 1 to 10, where 1 indicates no disease and 10 indicates plants almost killed by leaf spot disease. NDVI data was recorded using the handheld grain seeker, which uses the formula near infrared minus red divided by near infrared plus red. This NDVI value ranges from 0 to 0.99. Digital camera was also used to take plot features at the same time with the visual disease evaluations. The indices derived from the RGB imaging were the green area, the greener area, hue angle, and crop senescence index. RGB indices were extracted using breakpiece, Fiji components of the image software. ANOVA was performed on a raw data using APRES statistical package version 4.0.2. Tested means from the ANOVA were used for Pearson correlation analysis. Various components for manual and the ATP trace were estimated using the procedures described by Akinwale et al. 2010. Broad sense heritability was calculated by dividing the genotypic variance by the phenotypic variance. Expected genetic advance was also calculated by multiplying the constant, which is the selection differential at 5% by the phenotypic standard deviation by heritability. Results and discussions. The genotypes exhibited differences when it comes to early and late leaf spot diseases. The highest score for early leaf spot was seen at 85 days after planting, which ranged from 3 to 6 on the scale. The genotype 73-33 had the least score, while the genotype GHALL-AP-NK and others had the highest score, making genotype 73-33 a promising genotype aspirant in future breeding programs where leaf spot is in the equation. However, the highest score for late leaf spot was recorded at 95 days after planting and ranged from 3 to 7 on the scale. The genotype 73-33 again was part of those with the least scores, while the genotype Shitaoki had the highest score. The genotypes exhibited differences when it comes to pores per plant and pores weight per plant. Genotype OUG-ICGV SM02724 had 10 as the least number of pores, while the genotype GHA-ICGV 15008 had 19 as the highest number of pores. Lowest weights of 5.49 grams was obtained by the genotype MAL-ICG 14630. Highest weight of 17.5 grams was obtained by genotype ZAM-ICGV-SM-07599. Correlations among variables at 95 days after planting. From the table, it is observed that the ATP parameters, which were the greener area, green area, hue, crop senescence index, and the NDVI, had significant associations with the manual parameters measured, which were the leaf spot diseases, as well as the yield components. The highest of this association, which was negative, was seen between GGA at 95 and late leaf spots at 95. NDVI was also negatively correlated with late leaf spots at 95. The least of this correlation, which was positive, was seen between crop senescence index at 95 and late leaf spots at 95. And you come to the pod weight per plant. The highest association, which was positive, 0.62, was seen between the NDVI and pod weight per plant. So this means that this parameter, NDVI, indirectly can be used to phenotype peanut when it comes to yield components. When it comes to pores per plant, NDVI also had 0.55, which was also significant and also a positive association, which also means that the parameter NDVI has the potential to either complement or replace the manual way of estimating yield components. went further to calculate the heritability between these parameters. And so from this table too, we've seen that when you take the genotypic coefficient of the genotypic variances, they were higher than the error variances, which implies that the environmental influence on these traits was very low. And so the differences that we see in this data is attributed to genotypic variation. When you come to heritability estimates, we've seen high heritability between the parameters, that's the manual parameters measured. We have 91.91 as the highest, which was seen between the area and the disease progress curve for late response disease. And the lowest was 53.47, which was seen for cause per plant. When you come to the expected genetic advance, the highest of 37.11 was seen for area and a disease progress curve for late response disease. When it comes to the genetic percentage, the genetic advance as percentage of mean, the highest was also seen between pod width per plant. The highest was seen for pod width per plant, which was 49.89. And so this tells us the percent at which the gain can be improved. So this gain we are seeing here can be improved up to 49%. This is also the variance estimates for the high throughput traits. And similar results is also seen here. The genotypic variance are higher than the error variances. So this implies the variations that we see in this data as a result of genotypic differences, since the environment has less influence on their expression. When it comes to heritability, Browson heritability specifically, the highest Browson heritability of 93.03 was seen for green area at 85 days after planting. And we could see that most of them were highly heritable, except NDVI at 85, which was 0.41. When it comes to genetic gain, expected genetic gain, the highest of 29.69 was observed for hue angle at 95 days. When we also come to the genetic gain as percentage of the mean, we've seen the highest of 78.44, which was obtained by the greener area at 95 days after planting. And so when you compare these heritability values to the manual ones, we could see that the ATP traits at perform comparatively, they were better in terms of heritability than the manual one, which is a good thing in the sense that heritability helps breeders to select suitable plants from the lots.
We have 2 minutes left in the presentation.
So this is what I discussed from the table. Come to conclusion and recommendation. We've seen the significant association between the GGA and other manual parameters. So this association implies that indirectly we can use these ATP parameters to select for late response disease as well as yield components. And the better correlation that was seen between the ATP traits and the late spot diseases were seen at 85 and 95 days. And so the best stage to use this ATP equipment is at that stage, 85 and 95 days. The RGB disease exhibited comparable or better broad sense heritability to this visual scores, which indicates they can be used in breeding programs to increase genetic gain when it comes to selection for leaf spot tolerance. Future recommendation. This study should be repeated using area photogrammetry from a drone, as this will allow significant time saving when compared with handheld devices. This work was successful through the efforts of supervisors, Professor Kwajo Ofori, Dr. Jiman, Dr. Richard Otim Frimpong, Dr. Maria Balota, who is also the project PI, as well as Dr. Alexander Rice, Navy, Mr. Baba, and the students who also helped immensely, Mr. Jaffrey, as well as the financial contribution of Feed the Future. Innovation Lab. Thank you very much for the attention given.
Thank you very much, Emmanuel. We have time for one question. This question comes from Shyam Taluri. Question is, Emmanuel, how did you separate early leaf spot infection from late leaf spot infection in the plants or plots? Were they measured independently in separate plots?
Okay, so per the scale we use for the scoring, what we observed was that the early leaf spot disease occurred earlier, around 70 days to 80 days, but the late leaf spot occurred later part of the growing season. And so they were all scored differently. And also the symptoms are not the same. And so it's easy to differentiate between the two diseases.
All right, thank you. And that's the time we have. Thank you for your presentation.
Thank you too for the attention.